our next speaker, Dr. Hsiang-Wen Hsu. Hsiang-Wen Hsu, can you share your screen?
Yeah, thank you so much for having us. So I'm Shang-Chi, and from the Impact One Institute out of the survey located at University of Colorado, Boulder. We could have him having you here in Boulder, but unfortunately that's not going to happen. So here I show the team members of photo. So next time we'll see each other again. And this talk, Electrostatic Removal of Fine-grained regoliths on Sub-kilometer asteroids, here we try to address one of the issues that are shown here, that on the screen you see 3 different sceneries from 3 different places of airless bodies in the solar systems, and you might just know where they are, and they are very different. So we try to understand what are the processes shaping the surface, and what are the implications, what we can learn from this. And so, as mentioned, that Bennu is really, really rocky. So there is dominated by bouldery scenery, in contrast of the moon, of course, but also to the near-Earth asteroid Eros, which have ponded deposits and indicate a fine-grained regolith. And so this is a quite drastic difference. And if you look at these 3 bodies, one prominent difference is their sizes, which means the gravity is very different. So if you look at the moon, it's basically a planetary bodies, and it has a gravity in the order of magnitude of the Earth. And look at Eros or Bennu, their gravity is in much different regime. And it has been proposed that small bodies like in the Bennu Eros size could not retain thick regoliths because impact ejecta are just fast enough to escape the gravities. And unless you have sufficient gravitational well like the moon has, you will be depleted in fine-grained regoliths produced predominantly by impact. However, recent views somehow shift in the way that an important process, as mentioned this morning, that thermal fragmentations, that is the stress caused by repeated thermal cycles on these airless bodies, could actually produce fragments from the exposed rock. And in the Delbo 2014 paper, it shows that this is actually more effective a process compared to meteorite impacts. And there are indications seen by seen on Rugu and Bennu from these 2 fantastic sample return missions, showing that these quacks might really associate with these thermal fatigue fragmentation processes. And so we consider this is the first process we're going to include, and is independent of object size. So it's basically done by the heating process, not gravity. And the production rate is somehow, it should be tied to the influence of the sun and also the body rotation that determine the thermal cycles, and also what are the temperature change at different heliocentric distances. And the second process is we all familiar is the impacts. And as shown before, that the gravity is a big player here that would determine if these impacts are production or loss for the regoliths from regolith retention perspective. So for a moon, which have an escape velocity which is basically higher than 99% of the impact ejecta characterized by the LADI emissions around the moon, you can expect most of the ejecta will be retained, in contrast to small body like Eros or Bennu or Rugu. And but the other new information from the Hayabusa 2 small carry-on impactor experiment, which is showing clearly, is that there are also slower impact ejecta deposits around the impact crater newly created by these experiments. And so from this perspective, we basically took a really kind of order of magnitude estimate on the fragmentation rate to be 5 to the 10 to the minus 10 kilogram per meter square per second, which is roughly about 10 times lower than the terrestrial weathering rate that is somehow a weakly constrained parameters in the model, but somehow I think this is a good starting point. And the third process is kind of the main character here is the electrostatic dust transport. And it has many indications on airless bodies like arrows. You have these flatted, smooth ponded deposits indicating the presence of small particles, preferably located in the gravitational low locations, or on the 6TP CG comets that they have similar presences of these. And there are many models trying to understand how this is possible through electrostatic transportation processes. But one of the key ingredients in this model that has only been solved recently is how these particles are lofted. And at Colorado, we have serious experiments led by Dr. Hsu Wang. So let me start the movie. On the left, you will see this popcorn-like dust lofting from a crater under this high-speed video camera. And what we do is, this is at Earth, and what we did was shining electron beams onto these particles to simulate exposure of ionization radiation in space. And so what we get out from these sets of experiments is that how particles can attend significant amount of electrostatic charges to repel each other is because the presence of this microcavity in the porous regolith, that ionization radiation will allow the electrons to accumulate in these microcavities, which will accumulate until the repelling force is strong enough to expel the grains and destroy these cavities held by the particle cohesion. And this is the mechanism that has been tested in these serious experiments, and so far successfully explained a lot of what we observe in the lab. And one recent achievement just accepted on Icarus is that we can actually carefully, through analyzing these microscopic trajectories of each hopped dust particles, we can constrain their size and velocity relationship. And this allows us to quantify the mass loss rate that's driven by the electrostatic dust transportation. And you can see that these is a really slow ejection speeds, like a meter per second scale, and that will only affect the tiniest body in the solar system. So putting these two processes together, we can, and here shows the Bennu with an escape speed of 0.2 meter per second. That means a lot of particles will be able to escape the gravity from Bennu. And so if we put all these processes together, we get this plot, which is a little bit busy. So let me walk you through this. So in the vertical axis, it shows the regolith mass loss and production rate.
2 minutes.
Yes, great. And on the horizontal axis, it shows that vary as object size. And you can see the blue one is the production and the red one is the loss. And you also see different components. And what is important, of course, is the intersection of these two curves. And so if we look at another figure, basically the same thing, but we also examine the heliocentric distance relationship into this, you can see that at, for example, at 1 AU distance to the sun, the objects smaller than 0.8 kilometer in radii will predominantly lose their regolith. That means they will likely, with time, to be looking very rocky and bordery, just like what we have seen so far on Ryugu Bennu and to some extent Itokawa as well. And larger bodies will be able to retain their fine-grained regolith and be and so far that is consistent with what the objects we see. And more importantly, I would like to discuss the implications. So first, I think this is important in regarding for future explorations, for sample returns or for mining opportunities, and what kind of instruments or mission strategies you are going to apply for different type of objects with or without regolith. And second is that removing these fine-grained regoliths could have spectroscopic effects on their surface spectra observed on the ground or in space. And the confusing part is that removing the fines will actually give you opposite trends in contrast to the reddening caused by space weathering. And so these could be two competing effects, and that might need to be looked into, which we just submitted a proposal last month, fingers crossed. And third one is that this could also, changing the regolith property could also introduce changes to their thermal radiation effects, and that will affect the migration of small bodies, predominantly these ENA objects from their source region in the main belts, and how they propagate into near Earth space. And the good part and the best part about this is that we will have opportunity to examine this hypothesis in the next decades. And there are many opportunities. I will not repeat this. So that goes to another thing is that what we really need is ground truths from really characterize the properties of these electrostatic particles, not only in the lab, but also in space. And on lunar surface, there have been a lot of indication that of the presence of electrostatic activities, and an instrument development project led by Dr. Hsiang-Wen is focused specifically on this. So this is a summary that for sub-kilometer asteroid, we think the regolith loss due to electrostatic process dominates over the production from fragmentations caused by thermal fatigues and meteorite impacts. And this could have effect on the surface and physical properties of these tiny bodies, and which may be, and their implications need to be looked into regarding planetary defense and future studies. And in parallel to advance our modeling technique with this approach, we also really need is the ground truth measurement of the microscopic effect like fragmentations and electrostatic lofting grains properties. And that's it. Thank you.
Okay, thank you, Dr. Hsu. Because of our time limitation, we're going to move on our next speaker.